So happy Friday. So I want to finish up some of the stuff with the applications of the uniform boundedness principle. And it's got this beautiful little application about convergence of Fourier series. So let me just remind you, given an f in L1, let this guy equal the kth Fourier coefficient. By the way, L1 integrable one periodic functions, and this is the way I've defined my Fourier transform, like so. So we've kind of been studying this thing. The motivation for this comes from, it's really, if f is in L2, which notice is a proper subset of L1, this is the inner product of f with the orthonormal basis element ek. And so, the partial sum operator is what we call this guy. Like so, okay? And if we use our Hilbert space theory, then this thing converges to f in L2, i.e. this 2 norm of the difference goes to 0. Okay, and that's just that's part of this characterization of an orthonormal basis that we did. By the way, this is sometimes called the Rees-Fisher theorem, and so that's nice. Now, I guess you guys didn't do this last semester with DCU, but about the modes of convergence. But turns out if you have L2 convergence, you get a subsequence that converges almost everywhere. And so what we're interested in for the moment is pointwise convergence of Fourier series. So when does it converge pointwise? Well, like I said, this is Hilbert space. This is a result that obviously we don't have time, but turns out if you get L2 convergence, you get what's called convergence in measure, and that implies that there exists a subsequence that converges almost everywhere. So there exists a subsequence that converges almost everywhere. All right, but getting the whole sequence is actually an extremely deep thing. So if you can actually remove that little subscript k there, that is what's known as Carlitson's theorem, and it's a very, very deep thing. Sorry, this is a corollary of this. This is f in L2. And so, like I said, Carlitson actually removed this subsequence. It's one of the deepest theorems in analysis. He did it in 1966. Really, there's maybe been a couple other proofs of it since then, but that used his same machinery. It's kind of a crazy result. Okay, well, how about so forget about the almost everywhere, we can't really get a handle on which x and which ones it's converging. What if I just want to know, I want to like fix a theta, and I want to know, so this is pointwise convergence, but just say for a fixed theta. And I want to know, when does this happen? Okay, because so if f is in L2, you can't fix your theta because you only get like an almost everywhere. Well, this depends on the continuity properties of f, and for instance, if f is continuous at, you need more than continuous, if f is actually Lipschitz continuous. At, say, theta naught. And what that means is something like this. There's some constant like that. So as you know, this is a strong, it's sometimes called Holder continuity, but this is a strong version of continuity where you have the actual distance here. Okay. Then you get this convergence. Okay, and so you get that convergence. Hang on here, sorry about that. And by the way, it doesn't necessarily work if it's continuous. You can, if it's just continuous at theta naught, you can weaken this. There's something called the Dini condition. There's all sorts of, these are kind of undergrad exercises that you can do about when a Fourier series converges. But the whole point of today is to show actually that you do indeed need this stronger notion of continuity. Just continuous is not good enough. Okay. So, theorem, and this is with the help of the uniform boundedness principle. There exists f continuous one periodic function such that sup of the partial sums equals infinity. And so let me just think about this just for a second. So first off, f, this is an L1 and L2. It's continuous, so it's nice. It's bounded, everything. So its Fourier series converges. These converge in the L2 sense, for instance. However, they do not, if I pick this 0, I can find an f in here where that Fourier series diverges at a point. And by the way, the number 0 here is just for convenience. You could put d theta here and it works. All right, and so this is an interesting result, and we're going to just show the existence, I don't know, of a constructive proof of that. Actually, there are constructive proofs of this, I'm pretty sure. I don't know of one off the top of my head. But this is just going to be an existence result that we're going to get from the uniform boundedness principle. And so, let's do it. So first off, let's look at what this is. So what is this thing? So this is equal to the sum, k from minus n to n f hat of k. And notice here, if I'm doing that at 0, the exponential terms all disappear. Now they're in this, and so what this is equal to, and like I said, at this stage, the 0 doesn't matter. You can do any theta. And you can modify, well, one way to modify it would be to multiply by the theta, but this is f theta e to the negative 2 pi I k theta d theta. And now here's the point. This is a finite sum, so I can pull this integral in and out. And so I can pull the integral out, and what I get is f integrated against exactly the Dirichlet kernel. It's actually the minus, it's actually the Dirichlet kernel of d evaluated at minus theta, but the Dirichlet kernel is even. So this is what we get. And so here, what is this? The Dirichlet kernel, recall, is minus n e negative 2 pi I k theta. And if you look, pull the f and the integral out all the way, and you get this exact sum, except for the minus sign, but notice I can put a minus here because I can sum this from n to minus. I can reverse the order of summation to get this. And so, if you recall, you can also see that we did this long calculation about this thing. If you view it, if you kind of do a geometric sum, this is equal to 2n plus 1 pi k theta over sine pi theta. I think that's the formula we got. Okay, but this is interesting. So In other words, we've got this nice little formula. Let me write it here. So this is equal to f theta dn theta d theta 0, 1. Okay, and so this is kind of nice right here. So first off, let's define a function phi from here to just the complex number. So this is actually a linear function on this Banach space. This is a Banach space, and so we're going to define it by just set it equal to this thing. So basically, I evaluate the Fourier series, the partial sum of the Fourier series at 0, and it's equal to this formula. Just write it in. Okay. All right. Well, phi is clearly a linear function just by the linearity of the integral or linearity of these sums, however you want to look at it. And moreover, it's a bounded linear operator. And so why is that? Well, I can pull this in the integral. And remember, the norm we're putting on this is the L infinity norm. Okay, and so I can pull out, this is a continuous function, it's got bounded. And then I'm left with something kind of bad, the L1 norm of the Dirichlet kernel. Now, this is finite for each n, but remember we did this calculation that this goes off to infinity. Now that doesn't really help us a lot because this is bounded below by this guy, and that going off to infinity is bad. However, what this does imply, i.e., this is a bounded linear functional on the complex numbers, or sorry, on the continuous space of continuous functions, one periodic continuous functions, and moreover, its operator norm, which would be like if we took this equal to 1 and souped over all of them, the operator norm is less than the L1 norm of the Dirichlet kernel. Okay, so that's good. Okay, what we're actually going to do is get that it's equal to that. And if to do that is actually not too bad. It would be really easy if we could just take f to be the sign function, the signum, the sign in terms of plus and minus of the Dirichlet kernel. So take f to be 1 where this is positive, negative 1 where it's negative. Fortunately, that's not a continuous function. However, we can approximate by continuous functions. Okay, so let's take a look here. So what is this thing? Again, let me write this down. So this was the formula that we derived a while ago. Okay, and if you look at what this thing looks like, just in, say, 0, 1, looks like this. And I may have, like that. Okay. And then as n gets larger, basically it adds more oscillations here. But so what I'm going to do is I'm going to let g of theta equal 1 if dn theta is greater than 0. And let me do that. And negative 1 if dn theta is less than 0 and 0 otherwise. Now, just working the interval 0, 1, there's only finitely many intervals. And so here, my function basically looks like this. This will be my g in. Okay. This little piece right there. I shouldn't have drawn these little circles, but this will be my function. Okay, there's g. Alright, well, g is not continuous, but I can approximate it by a continuous function. We can get fj, which is trapped in between -1 and 1, with fj converging to g, pointwise. And so what's the f that will work? Well, what you do is you just chop it off a little bit. I shouldn't have drawn one. And I guess it's like that. So these blue ones are my fj's. Okay, and then what I can do is as j gets bigger, this just fills out. Okay. All right, so by the dominating convergence soon, what we have is that phi in fj, this thing, if I take a limit on j, and notice f in magnitude is less than 1, and so it's integrating as a Dirichlet kernel, which is in L1. I can pull this in and I get g dn d theta, and that is exactly the absolute value of d, which is the L1 norm. Right, this is L1 norm dn. Okay, and now, since we also have that these functions right here, the fj's, are less than or equal to 1, so they're suit norm. If I do the bound here by my norm times the L infinity norm of fj, this is 1. Okay? So I get this. And so the moral of the story is, if I take a limit here on j, I get the L1 norm of the Dirichlet kernel. And so I have, erase this nice little picture. Next time I draw that picture with maybe 2, n equals 2, which is, actually that probably was n equals 2. Okay, so anyway, what I have that the norm, this thing is a linear functionals. Norm is the L1 norm of the Dirichlet kernel. Okay. Now we're ready to invoke the uniform boundedness principle. So we know that as n goes to infinity, this goes to infinity. So the sup of n of this family of linear operators equals infinity. This is since, and this is the calculation we did the other day. Since that thus, by the uniform boundedness principle, so recall that uniform boundedness principle says pointwise implies uniform bounded. In other words, if you don't have uniform bounds, then there exists a point where you don't have pointwise. And f here such that sup in the end of f equals infinity, and this is exactly the way I define this. This is the partial sum operator evaluated at 0. So in other words, we get this f from the uniform boundedness principle. There just exists one, there exists some f. And so that's it. So let me just see how much time I have here. All right, so got a little bit of time. So just to kind of sum up Fourier series. So there's a Hilbert space theory. If you assume your function's in L2, then you can use the Hilbert space theory and you get this nice isometric isomorphism. And you can read through the notes. I've added the material back from the Hilbert spaces. On L1, well, you're no longer in L2 necessarily. So what happens is you land in sequences that go to 0 at infinity, plus or minus infinity. Well, it turns out you're not onto, and that's actually another deep problem with the Fourier transform is how fast does the Fourier transform the L1 function decay? In other words, can you describe the range of the Fourier transform on L1? And then finally, how about convergence of Fourier series? So now we're looking at the Fourier transform basically on the continuous functions, kind of the opposite endpoint. And do we always, for continuous functions, this thing's nice. Do we have convergence, pointwise convergence, say? No, not quite. You can actually, and this works, you can pick any point here. Like I mentioned, it's a little shift in the argument. But, so that's about all for the functional analysis. Next week, we're going to start into complex measures and move towards the radon-Nikodym theorem, finish up with the duality of LP spaces, and that'll do it for us. So everyone have a nice weekend. I'll see you all on Monday.